We looked at some examples for the ratio test. The next one says that if you take the nth root of the nth term and it comes out to be less than 1, that its conversion more than 1, then it diverges, and if it equals 1, the test is inconclusive. Now, for this test, sometimes it's fairly obvious when to use this test because the terms of your series will be defined pretty clearly with a power of n, right? So that if you take the nth root of this, that's just going to be a nice expression like 2n plus 1 over 3n plus 2. And then when you take the limit of that expression, in this case again, you can use the coefficient and it's going to be 2/3, which is less than 1, and hence this is convergent. Now again, over here, it's fairly obvious that you use the root test because you have n squared in the power. That's going to be 1 plus 1 over n to the power n. Right? Why? Because if you have something to the power n squared and then you take power 1 over n, they multiply, n squared times 1 over n gives you n. And then you apply this limit, and this is again a familiar limit. This is basically the definition of E, which is more than 1, which means it is divergent. Our general strategy to test for series, something like this, is the limit of the nth term not equal to 0. Yes, then it simply diverges. No, it could still converge. If it's an alternating series test, use the alternate series test. If it's not, is there n in the exponent? If there is an n in the exponent, you use the root test. If not, is it decreasing? Then you can use the integral test. If not, you use the ratio test. If it fails or inconclusive, then you use the comparison test. So this is just one way of thinking about it. There's going to be a lot of hit and trial involved in this process of finding or proving convergence and divergence of series.